Hey, morning, Calvin. How you doing?
Oh, I was doing better before the quiz.
Yeah. You have any questions I can help you with?
Um, like I I kind of know where I went wrong, but I've been having a hard time with like the surface charge stuff.
Okay.
But like I have, as far as quiz 4 went, I have like the E1 normal is equal to, and then the formula rho s divided by E1.
Yeah. Okay. So are you, just to make sure, you're still working on the quiz? You're looking at it right now?
No, I already turned it in.
Okay, you turned it in. All right. So the yeah, what you need to do is first you have, this set of boundary conditions, right?
Mm-hmm.
You have some boundary conditions, and the boundary conditions are for either two mediums where like you have one's a dielectric and the other is a dielectric, or you can have the other case where you have a dielectric and a conductor. So in this case, right, we're told we have a dielectric that surrounds a conductive metal cylinder. So that cylinder in there is metallic, and then
Mm-hmm.
surrounding it is a dielectric. And then in the that reference table below, you can see what the set of boundary conditions are, right? So we have two options. We have the field component, so we can, here, let me share my screen with you. Right, so we have, this says what you want to find. So this is what the field component, that just means, electric field or electric flux density, but both of these are vector fields. And then we can either choose if we have two media, so that's like two dielectrics, or we can have the medium with the dielectric and the conductor. So this is what we should choose, right?
Mm-hmm.
Okay, so that means then that we have, once we know this, okay, good. We've determined that we should be looking in this part of the table because this describes the boundary conditions for two different media. Now, what we want to know is what the surface charged is at the top surface.
Oh,
Okay. So,
yeah. Okay.
so,
Well, that would just be D1.
yep. And do we actually, yeah, and it's either D1N or E1N, and use the dielectric constant, which we also know.
Okay.
All right. Is this
Well, okay.
helping a bit?
Yeah, I mean, I think the part that threw me off really is when you put the E naught there, because I was confused on where to use it because I didn't use
Uh,
it.
okay.
And so that's the part where I'm like, I probably should have used that somewhere.
Yeah. All right. So what this means, E1, let me close this and open a whiteboard. So we have this is the dielectric permittivity,
Mm-hmm.
and we usually write it like this.
Oh, okay.
Now, the reason we do this, I, yeah, I think I like sort of talked about this, but maybe I didn't explain it completely.
No,
This,
you
okay,
did talk about it like that. The E naught is just the permittivity of air, and then when you multiply it by the R1, it'll give you that of the certain material.
yep, yeah, exactly. So E1
Okay. I forgot about that part.
So
Okay.
this is a physical constant. But this one is sort of made up. Okay. And the reason I say that it's made up is because people, right? Like since before we could measure things well, we wanted to be able to compare the dielectric constant of objects, or say how they're different in terms of their dielectric property. And the reason that we want to like even talk about that is because this constant, it describes like, you could think of it in a few, the constant you could say describes the way that the electric field like condenses inside of a material. Or you could say that this constant describes how easy it is for changes in the electric field to affect the movement of charges inside a material. There's a number of reasons why you might be interested in that, in this dielectric constant. And you see that in the world in places like semiconductors, right? We've chosen these lots of special materials like silicon, and then you dope it with special things. And when you're doing that, right, you're basically just changing this number on there, like how well, how resistant is this to like charges moving around in it. There's a bunch of stuff that you can do with this. So people prefer to they like to compare how different materials act with each other. Now this number, right, this is a weird number, right? 8.825 times 10 to the minus 12. No one wants to like constantly refer to this, such a weird number, right?
Right.
Units, farads per meter. It's really small. But this has no units. Okay, and the scale of this is usually 1 to maybe about 100 for a very exotic material. And when I say exotic, I mean stuff that's not found in nature. Like physicists and material scientists in labs cook something up that has a weird dielectric. So you can easily, with this number, the relative one, you can easily compare how two objects act without having to talk about this strange number.
Okay. Yeah. Okay. That makes sense. I definitely thought that I was way far away, but I was actually closer than I thought. So that's good.
It sounds like you're fairly close to it. And then two, I'm usually like on these quizzes, I'm not like typically trying to like, I'm not here trying to like give people zeros. Usually I try to like, I'm trying to distribute it from like people who understand the most to the least, but I'm usually not giving like zeros or really even like less than 5 very often, unless you are like really doing no work or like aggressively wrong in something. So
yeah,
try not to worry about it too much, but yeah, I don't know what else I can say to help. Hopefully that helps.
No, it makes sense. I mean, yeah, all I really missed was the fact that I needed to add that E1 is equal to ER1 E naught. So I'll write that down, or I've got it written down, so now I'll remember that. But as like far as like the test goes, is it going to be structured similarly to the quizzes? Like, I mean, in the fact that if you give us a problem, you'll have like a table of like formulas to use.
I think so. Let's see.
Because I know we have the cookbooks, but then even then, like there are instances like that table, for example. that's not in our cookbook specifically, where it's just in the book?
Yeah, so I think on the exam, there is another boundary boundary condition problem, and I have included the same table. So
Okay. Yeah, I was just wondering because I know in like the homework we did like the flow stuff through the and the permittivity of that. And I was
yeah,
just wondering if we had like a question like that, would you give us the formulas necessary? Or are there like things that we have to know off the top of our head?
yeah. So in the exam, what let's see here, let me double check all of this. It's a fair question. Um, I usually don't think memorizing formulas is very useful. So I usually don't have stuff like that. But of course, there's always this problem, right? Where sometimes I forget if you've like taught this stuff for a long time, like I have, you forget which formula is like, I just, randomly, know.
Mm-hmm.
Students might think is like, something that they should have known. Um, which is the reason that this is always a difficult question to ask or to answer. Um, okay, so once more people come up, we just have you and Gabriel right now, but basically all of the cookbooks are in the front, and then the table is in there. On the other problems, I would say there's basically not much additional information.
Okay.
Yeah, or like one of them does have a couple of the integral forms. Don't want to say much more than that,
Yeah, I
but
completely understand that.
I yeah, I think I usually like I'm usually writing all of these, so I think that they're fairly similar to what I think they're similar to what is in the homework. That's my
Okay.
but don't count on having anything more than those cookbooks in that table in printed into the exam.
Okay.
So yeah. So to everyone that's joining us, Calvin and I we were just talking about the exam a little bit. For that, we were talking about dielectrics, and in case you're interested, right, you could look this up. This Wikipedia article is kind of interesting, but these show you just some possible dielectrics of materials that exist in nature. So the reason, right, we like to often compare things based on the relative dielectric, and that's because the relative dielectric tends to be between 1 and, I had told Calvin that about 100, but there are a few things that are, very unusual, that are apparently very high. But most objects have their dielectric somewhere in this 1 to 100 range. And so that's why scientists like to compare these two different things using the relative permittivity, or this relative dielectric constant. It's an easier, faster way to compare objects to each other. It's still up on this whiteboard, and right, this epsilon naught, right, this is a physical constant, and it's very small and it has strange units. So that's why people don't want to constantly talk about an object's dielectric constant based on this, because you'd be comparing very small numbers to each other. Like even for example, if you were to compare, so let's just take 8.85 e to the minus 12. So if we were to compare these, right? So 2 times epsilon naught is, I just did this is 1.77 times 10 to the minus 11th farads per meter. So unless you're like a real freak with numbers, right, you probably aren't going to look at these two things and just be like, oh yeah, if the dielectric's 1.77 times 10 to the minus 11th, that's, you know, twice as big as epsilon naught. Like you could probably tell, but there's just, you know, you have the scientific notation. It's a very small number. You probably aren't going to be able to easily recognize that. And so because of that, we introduced this notation where we compare them all using this physical constant and then the relative dielectric, which is unitless. And then you can more easily compare things like you see on this table. It's a lot easier for us to look at this and see, oh yeah, you know, PTFE, this type of plastic, has a dielectric constant twice that of air. So beyond that, if you just notice, when you do start to see this is more of like a materials problem. But when you start to see some of these really high ones, water, right? This is a liquid. Glycerol, this is also another liquid. Ethylene glycol is a liquid. Ammonia, methanol, sulfuric acid. A lot of these are liquids, right? So a lot of these high ones are liquid objects. So that's something to be of note. But some of these other ones, I believe this, right? This is a powder. So just by looking at this table, you might notice, okay, this is interesting, right? That there's not a lot of things with a high dielectric constant that are powders or solids. And so that, I think, as far as I understand, this is like another whole field, you know, high dielectric materials. A lot of times I think these are used in, you know, things like special types of ceramics or other materials. So anyways, that's a bit about dielectric constants. There's a lot more that could be said, but I'll refrain myself. So anyone have any questions about the exam? So
is the exam this week?
Yeah, it's this week at the testing center. I double checked, actually only in Pocatello so far, but so the testing center, let's see. I'll show you, I'll give you, in case you haven't been there, I'll give you an idea of where it is. Okay. So, all right. So if you're taking the test in Pocatello, which I think most of you are, 5 of you are at least, right, you will go to this Gravely Hall. Okay. And this building is quite close to the engineering building, and you'll go over to this door. All right. And then you'll turn to the right and walk up these stairs. And this says it's in room 351. They told me that the exam would be in room 251, but basically there's a couple levels here that are all run by the counseling and testing service. So if you go over there to the 3rd floor, the 2nd floor, they should be able to point you to the right direction. So if you're on the campus there. Oops. Right, so from the engineering building, right, this weird metal sculpture thing is here. You just walk down this sidewalk, and then this is the door that you will enter. Okay, so you want to go to the door that's closer to the student union building. Yeah, so does anyone have any questions? Do you feel confident that you can find this place?
Yeah, so another question that I have is, are we doing it at 9 a.m. or do we have to call and schedule our own test?
Yeah, so what you need to do is you need to call them and let them know that you will be there on Thursday between 8 and 9:30. Okay. So what they told me is that within 24 hours of the exam, just verify what they said. Okay, so yeah, the students, yeah, so you should schedule this exam from 8 to 9:30 on Thursday. Okay. And you should call within at least 24 hours. So I believe you can call like today, right now, after this class, you can call them and tell them you want to take the exam on Thursday from 8 to 9:30. Okay.
So is the exam starting at 8?
Yeah, and I believe that's when they open. So so they should be able to give you some more information. But yeah, please take it between 8 and 9:30. And so you just call them and tell them that you're going to be there on Thursday from 8 to 9:30. And they, I guess, give you some kind of slot or appointment. So, and I suppose too, if you don't know where it is, you could, walk over there and schedule it in person so that you can figure out the exact location as well. And then into the exam, you can bring a calculator and a page of notes. So a page of notes that you have things written on in the front and the back. So you can bring in one page of notes. The cookbooks, all those cookbooks, so there's 3 of them, are included into the exam. So they'll be printed into that exam. So the one with all the vector information, that one will be included into the exam. The one with the vector calculus equations, and then the one with the electric scalar potential. Those will all be included into the exam. Okay. So I think, let's see here, if you look on Moodle, yeah, oh, okay. So this one is included, this one is included, and then I may actually need to update this. This one should be included and this one should be included. So that's actually 4 cookbooks. So I will double check on that to make sure that all of them are in there for this. Okay. And if not, then you could bring this edition. I'll let you know. Basically, just plan to have all the cookbooks in there. So that those will all be printed in there. And then what will also be printed in there is that boundary conditions table. So the same thing that was in the quiz. So in that quiz today, there was a table regarding the boundary conditions. See if I can pull it up. So this table is also will be printed into your exam. There's going to be 5 questions on the exam. So plan for that. That questions cover things from everything that we've talked about, although most of the questions are from the electrostatics. Okay. So there's really only one question that's more of a pure, based on the pure mathematics. Okay. So we covered a bunch of math for 2 or 3 weeks. So I did include one question on that since we did spend several weeks covering it. But the rest will be on electrostatics. And that makes sense because, right, most of the electrostatic stuff, we're using the knowledge from the calculus that we learned and we're applying it. So, okay, what else can I say? What's that? I think that should be, oh yes, the other thing I spoke with Calvin about. So if there are other equations that you think you might need, right, make sure to write those on your paper. So I included those cookbooks, but on the other problems, if you think there's things that you might want to remember, other equations or relationships, you should write those down. All right, so any questions from you about this now that we've talked about this for a minute? Okay. So today, right, this is for you guys. So whatever questions you have, ask them. And if there's no questions, then we will just end the class. So that's basically the structure for the rest of the class. So I'm here to help you study, answer any questions that you have, direct you in the right direction, etc.
I just have a quick question on the boundary conditions.
Yeah.
So for one of the assignments, it was easier to like tell what boundaries they were referring to because they were labeled completely.
Okay.
The direction of the vector and all of that. So how do we connect those boundary conditions to the ones like the one you give us in the quiz this morning? How do we know which plane is which and which is tangential? Or do we just make that up ourselves?
Yeah, great question. So all the boundary conditions, so whenever you have a boundary condition problem, you should look at the problem and you should try to determine what the two materials are. So what is the type of material that you have a boundary in between, right? So in the quiz today, right, it said that the boundary was between a conducting
Dielectric.
object and a dielectric object, right? So when you have the boundary condition, so you should determine the material types that you have. And the reason for that, let's go back and take a look at that table. And the reason that you should do that is because we have on the table of boundary conditions, right? We have two different categories, right? And this one is any two media. So this is two dielectrics. And then on the other side, we have one dielectric and one conductor. So first you should determine the two material types that you have. Okay, and then second, let's look at this table. And we can kind of break this up again, right? So we have the tangent conditions. And we have the normal conditions. So you should be able to look at the object. So wherever your boundary is, you should be able to determine what is tangent and what is normal. Right, so you should determine the material type, and then you should determine what is normal and what is tangent. Because first, when you determine the material type, you'll figure out whether you should use this set of equations, or if you should use this set of equations, right? So that's the first thing. You should determine whether you're using this one side or this side. And then the second thing you should do is you should figure out what's normal and what's tangent, because all of these boundary conditions are based on the normal and tangential components of the electric field. So you have a relationship between field 1 and field 2, which is the field in media 1 and media 2. And in order to find that final relationship, you're going to need to know what the normal part and the tangent part of the field is. Because you're either going to know, right, in all these cases, you'll either know something about E1 or about E2, right? And the boundary condition, this type of problem is just a way of translating your knowledge about one field into knowledge about a second field. So if you have knowledge about the field 1, the boundary condition helps you translate that into knowledge about the field 2. And that's what all of these are doing, right? You have knowledge about field 1, you could use that to get knowledge about field 2. Or if you had knowledge about both the fields, you could use it to get knowledge about the material used in the other media, right? So that's what these boundary condition problems are typically doing, is you have some knowledge about one field or one material, and you're curious about the other field or the other material, and you use the boundary conditions to determine them. And so I think your question, if I remember right, I've given some extra explanation, but is how do you know what these are? Is that basically your question, Daniel? How do you know what's normal and what's tangent?
Yeah, because like it labeled it as E1, E2, and those were not on the diagram. I was like, do we just make it up, or
Yeah.
an expected way to have it?
Okay, so if you're on a cylinder, right? What is the normal component to this at the top part of the cylinder?
Z.
I couldn't quite hear you, but I'm assuming you said Z hat.
Yeah.
Yep. Yeah, so that's correct, right? At the top part of the cylinder, the normal vector is Z hat. Now, if we're still, let's remain in cylindrical coordinates. Let's go to the side of the cylinder. What is the normal component to the outside of this cylinder?
R hat.
Yep. Yeah, this is R hat, right? R hat is normal. Now let's take this same cylinder. Let's chop it in half. Okay. Oops. What is the normal component to this? So let's think about this surface. So we have cylindrical coordinates. Oops. Okay, so if I'm on this surface and I choose a vector and it's R hat, that will be in this direction, right? Is that normal to the surface?
No.
No, it helps build the tangent component. What about if I point a vector straight up in Z? Is that normal to the surface?
No.
No, it's not either, right? So these two form the tangent. So what must the normal component be?
Phi.
Yeah, it must be phi, right? It's the only one we have left, right? So no matter where you are on this surface, if you choose the vector in the phi direction, it is normal to this sliced cylinder. Okay. What about, right? And we could do this. So I'm not in this class, right? In your calculus class, you already found, you probably spent several weeks finding normal and tangent surfaces. Does that sound familiar? In calculus 3?
Yeah, a little bit. Yeah.
Yeah.
Been a while.
Yeah, I'm sure it's been a while. So you can do this for any complex or exotic structure, right? Like if we just looked in 2 dimensions, X, Y, right? We could find this. It's not as easy to do, but this is something that you did in your calculus class. You could find the normal to this surface in this class. So this is Calc 3. In our class, we'll stick with some of the simple ones. Okay. And I say simple because we're dealing, in this case, right, this is a cylinder in cylindrical coordinates. And if we did the same thing, right, we would deal with like cubes or rectangles in cylindrical or in Cartesian coordinates. Okay, so what's the normal for the top, this top part? Let's say let's use our standard coordinate system. What's the normal component to the top surface?
Z.
Yeah. All right, so Daniel, are you starting to get the hang of this?
It's not the direction of the normal. It's more of which one is E. So we have the cylinder, right? And we have two materials.
Mm-hmm.
So which one do we, because I couldn't tell which one is which. I couldn't tell which one was the dielectric and which one was the conductor and which one is E1 or E2.
Okay. All right, let's take a look specifically at that then. All right, so the problem, this is the problem, and it says medium 1 is a dielectric that surrounds a solid conductive cylinder, medium 2. Okay, so let's just read this and let's break it into two parts. So we first read material 1, start here. So we first read this part, material 1 is a dielectric that surrounds a solid conductive cylinder. So it surrounds something, and then a solid conductive cylinder, a solid conductive cylindrical medium 2 has a surface charge density. So from reading this, we can just see that the medium 1 surrounds a solid conductive cylinder. And the solid conductive cylinder, right, is here, drawn in this diagram, right? And the medium 1 is all surrounding it. So this is medium 1. And this one, here, I'll change this to green even. Is medium 2. Okay. And then we're given that the field in medium 1 is given by E1. So we know what the field is outside. Okay. All right, so I think for this, perhaps if I had, maybe the confusion was that because I drew the figure, it wasn't clear to you what was going on. But if you had drawn the figure yourself, hopefully by reading this, you would draw some medium that completely surrounds a conductive cylinder. So I'm not exactly sure.
Yeah, it makes sense now.
Yeah. So sometimes if the diagram is given to you, it may be worth it to draw the diagram again so that you can completely understand what's going on. And then going back to my kind of rules is determine the material type. And so we determined, right, medium 1 is the dielectric and medium 2 is a conductor. So we must be in this realm, right? We should be using this side of the table for sure. And we're trying to find this surface charge density. So looking through here, let's see, the tangent fields, those are 0. Tangent flux density, those are 0. Then when we get down to here, we can start to see, okay, these two equations, right? These ones have information about surface charge density. And then this one, this equation, right, has electric field, surface charge, and a dielectric constant, right? So you should be able to kind of zero in on the idea that this is the equation that you want to use. That's the boundary condition. Okay. So you feel good? Feel confident on this now?
Yes.
Okay. How about everyone else? Calvin, feeling good about this problem now?
Yeah, I understand it a lot more.
Yeah. How about Cade, Mario, AK, Gabriel? All right, how are you guys?
Yeah,
feeling?
that makes more sense.
Okay.
Yeah, it makes sense. Yeah, only thing I wanna ask is like, when where it says E1, E1 to the T and E equals E2 to the T equals 0 for the tangential E and tangential D as well. It just equals 0. Does that mean you just don't have to worry about the tangential components anymore?
Yeah, what that means is that the field in both directions is equal to 0, and that's just because at the surface of a conductor there's no actual field,
Right.
is going to exist. So it's kind of a shortcut for saying, let's say that E1 tangent, and don't forget these tangent fields, they're always, you must express these in vector form, and that's because the tangent at the very least must be composed of 2 vector directions, right? Because in order to create a surface, right, if you just think back to calculus, in order to create a surface you need at least 2 variables. And so the tangent fields, that's a surface field, so you need at least 2 variables on this. So let's say that the tangent field is in the x direction, and then 1x. So sometimes if E1x is equal to 0, right, and this is a scalar magnitude, so it's a magnitude which is scalar. Also, I apologize that my pen is really sloppy today, so hopefully you can still read it. So in this x direction, it's the magnitude or the scalar of the component. And E1y is equal to 0. So if both the magnitudes are 0, so in this case, you sometimes see it written as, even though it's a vector, you sometimes see it written as just being equal to 0, like it looks like a scalar. And that is what is going on in here. And it's just saying that every component every component of the vector field, the magnitude of that component is equal to 0.
Okay. That makes sense.
So that's what that means. And so the tangent field must always be a vector component. Whereas if you look down here, right, these the normal parts, they simplified this into the scalar components, and that's because the normal part is has you can deal with it just in one, it's in one direction, and so you could deal with just the simple magnitude of that direction, that directional component. Okay. I think you might have got this out of the textbook too, but if you have the reason for this, I'll try to give you an intuitive explanation for why these exist. I don't know if this will help or not too much, but hopefully it will. Let's say you have medium 1 and medium 2 like this. Okay. And in medium 1, right, you have E field 1, and in medium 2, you have E field 2. Now let's just take a path, okay, around this. Let's follow it around. And if we followed this path around and integrated this, so if we were to follow the path all the way around and integrate all along that sum, right, we would be able to come up with a relationship between that path and the amount of charge that's contained in there. Oops. Let's see, I think that the book even has a picture of this. So if you look in the book, this is their little picture of this. But if you were to do that, you could go all the way around some closed path in there, and you could integrate your field around it. And when you do that, right, you know that for a static electric field, right, and we're in electrostatics, if we do this, this potential is going to be equal to 0. And that's because, right, this integral is equal to voltage. And so this is basically saying, right, if you have a multimeter and you put both of the probes at the same spot, the voltage will be equal to 0, right? So that's basically what this is saying. If you integrate all the way around here, it will be equal to 0. But you also know this relationship, right, that the divergence of the electric flux density is equal to the charge contained. And so if you were to basically then take a volume of this and make it smaller and smaller, just shrinking it down, eventually you would find the amount of charge that's contained on there, and that would be a tiny little bit of rho s that's in one point on the surface. Yeah, so that's kind of just a little bit of a bird's eye view of what's going on, or where these boundary conditions come from, but they come from looking at a surface between two media and considering the potential and the divergence of the fields at that. And that's how this, everything in this table came to be. Any other questions?
Could we really quick run through like a surface charge of a cylinder problem?
Sure, like, how much charge it is, or,
I guess it's a volume charge density, like in the exam practice 1, question 4, 5. Those are both very similar.
yeah, and then too, did you all see that I added a bunch of like basically solutions or information on how to solve all those practice problems?
Yeah, I did see that.
I'm happy to go over them. I just wanted to make sure everyone knows that. Okay. All right, so there's a infinitely long, uniformly charged cylindrical shell in free space, inner radius, and an outer radius. The shell has a volume charge density. Okay, so this has some volume charge density. And this, the units on this right are coulombs per meter cubed. So if we wanted to find total charge, right? That would equal the rho v times the volume. Does that make sense?
Yes.
Okay. So that's basically the same as saying Q does that follow?
Yeah, that makes sense.
Okay, so basically, if you want to know the total amount of charge in a volume, look at every little point in the volume and just add it all up. And that's what the triple integral does. It says, first add it all up along this direction, then add it up all along this direction, then add it up all along this direction. And pretty soon you'll have the total charge. Now this problem is in the most easily solved, probably using the Gauss's law. And so all right, so if you have this problem, right, we could draw it like this, where we have an overhead view and we see, yes, indeed, we do have a symmetrical case. So then we would take a look and we would start with this equation, right? That another form of finding the total charge would be to do this surface integral, this closed surface integral of the flux. to find the total charge. And so we would come up with this other relationship, right? And this is what we use for all the Gauss's law problems, where we say the total charge is equal to this closed surface integral of the flux density dotted with the surface. And then we would need to find the ds and the d. And in this case, right, this is another thing similar to like what we talked about previously, where in this problem, right, you would also have to identify the normal component, which we did. As r hat. And then we have a couple different regions that we should consider. So we should find the dr for all these different regions. So when it's less than, when r is less than a and we're in the center, there's no charge in there. So without even doing the integral, we can realize that there's no charge contained inside of here. And so the dr will be equal to 0 and the electric field would be equal to 0 inside of there. Now for the second part, we would then want to look at, let's find the dr, let's find the magnitude of the electric flux density when we're in this region where all the charges exist. So if we're in between this region where all these charges exist, let's see if we can find the magnitude of the electric flux density. And we will do that by solving for the total charge that's contained in there. Okay, and when we do that, when we're between A and B, there is a little trick, right? So on the phi limits and the z limits, right, we know for sure that we want to go all the way around, right? So this is a complete full circle. And on the z limits, we know that we want to contain the top and the bottom, which we'll just call L half to minus L half to L half, which is basically taking a slice of this. But for the R limits, we are somewhere between here, which is A, and here, which is B. So if I want to find the electric field here, we'll just say that this is at some point R, and the R is a variable. So we'll integrate up to a variable point. Okay. So the mathematicians, they might hate us for this, but we'll do it anyways. We'll integrate all the way up to this variable R. And that's where we get this from. So this variable R is when the R is somewhere between A and B. And so if we solve completely for Q, we'll get to this expression for Q. Yeah, sorry. Yeah. Get to that expression for Q and then rearrange so that we can have this value of the electric flux density at that when we're in between A and B. Is this making sense so far?
Yeah, it does.
Helping you? Okay, so basically we're doing, and I think, yeah, right, we have this, the left-hand side and the right-hand side of the equation that we start with. So we start with this equation, right? We have the left-hand side and the right-hand side of that equation. And we first solved, right, this, the right-hand side of the equation, right? And when we solve the right-hand side of the equation, I'm not sure if I included that here, but that's this part. And sorry, I think I might have skipped showing you that step when I was walking through it. So when we solve that right-hand part of the equation, I did skip it, I'm sorry. That's what this step is on the homework, or on the practice solution. Right, this is the right-hand side. And we solve this part of the solution, right? We figured out the ds and we figured out the d. So we took the ds and put it in here, took this d, put it in here. Do this, use those same limits. And that's where we come up with this expression right here, which this is the, right here, this is the right-hand side. And this is the left-hand side here. So we solve the RHS once. And we solve the left-hand side for each region. Right, and then we solve for the total amount of charge in each region. So in the first region, there's no charge. The second region, we're somewhere in between where the charge starts and where the charge ends in the radial direction, right? We're traversing this direction. We haven't got all the way, so we're gonna use this little substitute dummy variable r to come up with an R dependent equation for Q. So we use this little dummy variable r so that our equation for Q depends on how far out we've gone. But then in the final case, right, when we have got to R is greater than B, so we've gotten all the way to the edge of the cylinder, we've integrated all the way from A all the way up to R, where R equals B. So once we've finally integrated up all of this charge, figured out the total amount of Q, that is when we would get to this step. So in the third case, right, we need to integrate all the charge. And that's why the top limit is B and the bottom limit is A. And that will include every bit of charge from A to B. And so the total charge in that region is here. And see, this has no R dependency. The total charge has no R dependency. But when we go and put it into when we take the Q and substitute it, right, because dr is equal to the Q Sure, I get this right. Over Q over 2 pi RL. Right, so our DR has this R dependency, and that's why our field magnitude is still going to have some R dependency, is because the field has R dependency. And that is why at the end, when you get to the final result where you come up with expressions for the electric field in each of the 3 regions, all 3 of them are these two. These ones have that R dependency, and that's due to the fact that we know that we determined from the very beginning that there was going to be this R field dependency as we get further away. But in region 1, 2, and 3, we can find the Q, the total charge contained within that region. And some of those regions have R dependency, some of them do not. And that's why we arrive at this expression. Okay, so hopefully that helps. If you want to stick around, I can continue to talk about this. If you want to take off, feel free to do so.
Just real quick, Professor, what time are we supposed to set up our appointment?
Yeah, please set it up for the normal class time, 8 to 9:30.
All right, thank you. You have a good day.
Yeah, thank you. You too, Mario.
Thank you.
What's the time limit on the exam? Is it an hour? or-
90 minutes.
Okay.
Yeah. Mm-hmm. Feeling good? Ready to crush it?
I still need some practice, but I'll be
Okay.
good.
Well, check out those practice problems, and hopefully that'll help you while you study.
Thanks.
I believe in you. You'll kick its butt.
Have a good one.
All right. You too. Take care.